6.5a, we're going to extend what we've been learning with geometry of curves to volumes of revolution. Specifically, we're going to ask the question of how do we determine the volume of a solid that's produced by rotating a function around a certain axis. Okay? So today we'll look at the first method, what we call the washer method. In 6.5b, we'll look at what's called the cylindrical method, and then along the way we'll look at how we can distinguish between when to use the washer method and when to use the cylinder method, specifically after we encountered both methods at the end of 6.5b. Okay? So visualizing the washer method, or as it's also known as the disk method, okay? So the idea right here is that we're going to take a function f and we rotate it around the x-axis to produce a solid. This is useful for producing solids of arbitrary shapes that we may encounter in engineering or physics, specifically engineering with 3D printers, where you need a specific function in order to produce a specific shape. So if we want to determine the volume of this specific solid that's produced by rotating a function f around the x-axis, we can take note of the following, okay? So the volume of the solid can be broken up into thin disk of thickness dx and radius f of x. So we can take note of right here that the radius is f of x, our height right here at the certain x value, and that this disk has a thickness dx, okay? Akin to how a stack of pennies consists of individual disks of pennies, okay? The volume of dV of an individual disk is going to be given by the area of the circle times the thickness, or the area of the disk times the thickness, which in this case is going to be pi f of x squared times d of x. And the reason being is that we have pi r squared, where r is the radius, which in this case is our function value at x. So we have pi f of x squared d of x. So this represents the volume of an individual disk or an individual penny. All right. So now what we're going to do is, in order to find the total volume V, we can add all the individual volumes dV over the interval of interest a to b together using an integral. Again, recall that an integral geometrically adds areas together under a curve f. In this case, instead of adding areas, because we've rotated, we're now adding volumes. Okay, so this is like adding the area of each individual penny together to get the volume. Excuse me. This is like adding the volume of each individual penny together. Okay, to get the volume of a whole entire stack of pennies. Okay, so this method then tells us the volume is going to be equal to definite integral from x equals a to x equals b of pi f of x squared d of x, where we can factor out the pi because pi again is a constant. Okay. So this is the disk method in a nutshell. This is the equation that we need to know for the disk method. This right here will provide us the volume for a curve that's rotated about the x-axis to produce a disk. All right. So visualizing the disk and washer methods now, okay? So let's say now instead of having a disk, okay, we have an outer function f of x and we have an inner function g of x, so like we looked at in 6.4, okay? If we rotate this around the x-axis now, okay, or excuse me, better said, we're now looking at the area between f of x and g of x. If we rotate this around the x-axis now, what's going to happen is this space between g of x and the x-axis is going to be hollow, and then we're going to end up with a volume between f of x and g of x. We're going to end up now specifically with a shell that has a thickness governed by the width between f of x and g of x. So the inside of our shell is hollow. We have this thickness here, okay? So we want to determine how to determine the volume of this shape that's produced. So what we can take note of right here is that it's the same philosophy as taking the outer area of f of x and subtracting the inner area of g of x. It's like we're taking the outer volume of f of x when it's rotated around the x-axis, and we're subtracting the inner area of g of x when it's rotated around the x-axis. So we have that our overall volume is equal to the outer volume minus the inner volume. Okay? So we recognize that the outer volume is equal to pi times the definite integral of f of x squared, and that the inner volume is equal to pi times the definite integral of g of x squared. So as a result, the volume of our washer is going to become, we can subtract these two integrals right here, and we get that v equals pi. We can factor out pi since pi is on both of these integrals right here, times the integral of f of x squared minus g of x squared dx. Please note that the square is on both f of x and g of x. It's not f of x minus g of x squared, it's f of x squared minus g of x squared. So square is on each individual function. It's not f of x minus g of x and then squared. Okay? So this is the washer method. We call it the washer method because it's hollow like a washer instead of like a disk which has a solid center. Okay? So please note that if your inner function g of x is equal to 0, aka it's just the x-axis, No volume is subtracted, and the equation reduces to the equation for a disk, okay? So g of x becomes 0, and then we're just left with f of x squared, so it reduces to the equation for a disk. So this equation does make sense right here. The functions f and g are squared separately, so again, it's f of x squared minus g of x squared, not f of x minus g of x and then squared. And then f of x is regarded as the outer radius, and g of x is regarded as the inner radius, okay? So while solving volume of revolution problems, here's our step-by-step procedure. The first thing that we need to do is, again, determine the bounds of integration. So there are two forms that can be encountered. Again, we have the area bounded by upper and lower bounds, x equals a and x equals b, or we have the area enclosed by points of intersections between the two curves. In this case, we write out the coordinates of the point of the intersection, just as we've been doing, okay? So problem-solving process is very similar to 6.4. Now what we do is we determine the outer radii function, the inner radii function. Different from the area between curves, test points will be used to determine the inner and outer functions, okay? So inner and outer functions does not necessarily mean higher or lower functions. It specifically means what function is closer to the axis of rotation, which will be our inner function, and which function is further away from our axis of rotation, which will be our outer function, okay? So it's not necessarily the same thing as greater value and lower value functions. If the problem asks for the volume between a function and the x-axis, then again, same thing as with 6.4, then g of x will be equal to 0, the x-axis, and the washer method reduces to the disk method. We write the resulting integral for the volume, and then we evaluate the integral. Sometimes the volume integrals will be too difficult to solve by hand, and in that case, you'll set up the integral and solve it using a calculator. Other times, the integral will be simple enough to evaluate by hand, okay? And we'll take a look at examples of that in class. So example 1, disk and washer method, okay? Determine the volume generated by rotating the area enclosed by negative x squared and x minus 2 about the x-axis. So again, the first thing that we have to do here is determine our bounds of integration. Here we're not given x values for bounds of integration, so we're given, so we have to determine the bounds of integration by determining the points at which our curves intersect. So same thing as 6.4, we set negative x squared equal to x minus 2, and we solve for our x values representing the points of intersection. So we add x squared to both sides, which gives us 0 equals x squared plus x minus 2, which gives us x plus 2 times x minus 2, or x equals negative 2, x equals 1. All right? So now that gives us our bounds of integration. So now what we're going to do is the same thing as before, where we're going to use a test point, okay, which gives us x equals 0. And so we're going to use x equals 0 here, or any point between x equals negative 2 and x equals 1. So using x equals 0, we see that y minus x squared becomes y minus 0 squared, or 0. And we see that y minus x minus 2, or y equals x minus 2 is going to become 0 minus 2, or negative 2. So if we draw a graph to illustrate right here, okay, we can see that negative x squared is going to be closer to our axis of rotation, whereas x minus 2 is going to be further away from our axis of rotation. So as a result, negative x squared is our inner function, while x minus 2 is our outer function. So this illustrates a very subtle important point, is in that our inner function is not necessarily always going to be, and our outer functions are not necessarily going to be the greatest value function and the lowest value function. So in this case right here, x minus 2 is our outer function, but it is not the greatest value function. It's the lowest value function. Whereas negative x squared is our inner function, but it is not the lowest value function. It's the greatest value function. So we have to distinguish between those two subtleties. So we're looking at what is the inner function and what is the outer function compared to our x-axis. In this case, negative x squared is our inner function, and x minus 2 is our outer function. So now what we're going to do is write our definite integral here, okay? So we're going to have v equals pi from negative times the definite integral from negative 1 to 2 of our outer function squared, x minus 2 squared, minus our inner function, negative x minus 2 squared, okay? So as a result, we're going to get this is going to be equal to the definite integral, pi times the definite integral from x equals negative 2, x equals 1, of x squared minus 4x plus 4 minus x to the fourth. So what I've done right here is I expanded out the x minus 2 squared to get x squared minus 4x plus 4, and I expanded the negative x squared squared to get x to the fourth, okay? So now I can use the fundamental theorem of calculus to evaluate this definite integral, okay? So we're going to get pi times x cubed divided by 3 minus 2x squared plus 4x minus x to the fifth divided by 5, and that's give us our antiderivative, and we're going to take the difference of this antiderivative between x equals negative 2 and x equals 1. So as a result, doing a bunch of calculations right here, which I'll leave you pause the video if you want, but at this point we're pretty used to first fundamental theorem for calculus. This is going to give you a bunch of numbers that you can crunch, and then at the end of the day, these bunch of numbers is going to reduce down to 21 minus 33 over 5 divided by times pi. Okay, so this is actually a relatively neat example. Okay, albeit a little bit more dirtier version of a neat example. Okay, more difficult examples you'll do by hand, and then more straightforward more difficult examples you'll do by calculator, and more difficult examples, more straightforward examples you'll do by hand. Okay. So axes other than the x-axis, okay? So let's say now instead of revolving around the x-axis, we're revolving around the axis of rotation y equals y naught, okay? So in this case right here, what's going to happen is that we're still going to use the test points to indicate, to determine our inner and outer functions, okay? And again, that's why we have to plot our test points and compare it to the axis of revolution, because that will determine for us which function is our inner and outer function. Except now, if we're revolving around a line y equals y naught, okay, our outer radius now, instead of being just f of x, is going to be f of x minus y naught. The reason being is that our typical outer radius is f of x, okay, but in this case right here, we can see that instead of going all the way to the x-axis, we're going strictly to y naught. So we're going to have y naught subtracted from f of x to get our new outer radius, okay? Similarly, okay, our inner radius now, instead of being g of x, okay, if we look right here, our inner radius, again, is typically g of x, the height from our function g to the x-axis, but except now in this time, we're not going all the way from g to the x-axis, we're going from g to y naught. So in this case, we're going to subtract y naught off g of x to get our inner radius. So our inner radius in this case is g of x minus y naught. So our outer radius is going to be our outer function minus y naught, our axis of revolution, whereas our inner radius is going to be our inner function minus y naught in this case. Again, when we're revolving around axes other than the x-axis. And then as a result, our new arrangement is going to become outer radius squared minus inner radius squared, where our outer radius now is going to be our inner function, our outer function minus y naught, our axis of revolution, and then our inner radius is now going to be our inner function minus y naught, our axis of revolution. Okay, so that's the only change we have to make for axes other than the x-axis. If we're still a little bit unused to this, we're going to get more practice with these practice problems in class. Again, the idea here is just to expose you to the initial ideas and plant the seed for when we start delving into practice problems in class. And this is 6.5a.